Hello everyone, this is Dr. Chiranjeevi Manike, Professor in Data Science and Cybersecurity Department, MLR Institute of Technology, Hyderabad, as part of Deep Learning video lecture series. So in this lecture, we are going to discuss mainly one example, that is numerical example, that is to understand the perceptron. So previous class lecture we discussed mainly the basics, what is the definitions of a perceptron, what is a artificial neuron, and what is artificial neural network, and etc. So in this, so we are going to discuss again, we would recall the definition of a perceptron, and then we see the example perceptron, how training would be done. So in training, in performing the training process, how weights and biases would be updated, and we'll also see the examples like how we can represent a perceptron, that is to mimic the logic gates like AND OR gates. So let us quickly recall the basic definition, that is one definition of a perceptron, that is it is a simple neural network that classifies the inputs into the two categories. It's a basic perceptron that performs the task like this. So it is a simplified model of a biological neuron, and it was introduced by the Frank Rosenblatt in 1957. So that is about perceptron. So let us again go to the basic the building block of artificial neural network, that is a perceptron or a single neuron, and we already discussed how it takes the input and how it produces the output. So let us quickly and recall the mathematical part behind this, how this information, like suppose we have the inputs, so these are this x1, x2 and so on, xn, and also the bias, these are the inputs, and the corresponding weights like w1, w2, w3. So these are the weights, and then these are the inputs, and this is sum. So in this, so I would write like sum of this, so sigma I equal to 1 to n, there are n inputs, so xi times wi, and also we have to add this b, the bias, so we can add bias, and then this is a non-linear activation function, so this need to be passed to this nonlinear activation function z, so then that produce the output y hat. Okay, this is what we discussed in the previous lecture. This is how the inputs and are multiplied with the corresponding weightages, and how a term bias would be added and then passed to the nonlinear activation function. As we discussed, this bias, the term bias is introduced to shift the activation function left or right, and this activation function is mainly used in this to introduce the nonlinearity. So suppose if there are few examples, so first the thing in machine learning or deep learning models, so we have to train the model. So first we perform the training and then testing and validation, etc. So what would be done in this training, how deep learning models, are, let us say like the basic the building block of artificial neural network perceptron would be trained. Like suppose you can take any example, let us take a classification task. let us take a classification task. So, and for that, we like suppose we have some data, we have a data set. So data set has some samples, like let us say there are two features of each sample is described using two features, and there is an output, and these are x1 and x2. So there are some values like 1 0. Let us take binary values. So 1 1 0 0, like, and suppose if you consider this as OR gate, so then the output for this input and 1 and 1 and 0. If both the inputs are 0, then output is 0, then remaining all conditions output is 1. So suppose if you want to train on this data set, that is to build a perceptron to act like a logic gate. So in this case, we have considered the two inputs, x1 and x2. So there will be two inputs. So let us take, let us just consider only these two inputs. That is to understand this, how this we can construct this perceptron that represents the logic gate. So the two inputs and the corresponding weights. So then the value, like suppose here x1 plus x2, and that is like a weight. Let us initially take the random weights w1 equal to 0.5 and also equal to w2. So both w1 and w2 are the same. That is initially the weights are assigned 0.5. So in this case, like, and if you like bias is 1, so then we substitute the values, like this is y hat. So 1 plus, so that is x1. X1 means if you take the first sample, so 0.1 times 0.5 plus 1.1 times 0.5 plus then second input, that is 0, x2 equal to 0, 0 times 0.5. So then, and it produce the value. Okay, so whatever the value returned by this nonlinear activation function, and that must and should be either 1 or 0. So if it is correctly classified, that means as per the logic gate of end logic gate, so or logic gate, here this is a truth table for the or logic gate. So it has to produce the correct output. Like suppose the input is x1, x2, that is 1 0, it has to produce 1. If it is 0 1, it has to produce 1. If it is 1 1, it has to produce 1. If it is 0 0, and it has to produce 0. So that is the way. So suppose, like, let us say the output that is produced by this nonlinear activation function. So here we have to design a nonlinear activation function in such a way that, like, it has to, like, for example, if you consider this, like the weights are, suppose weights like w1, w2 equal to 1. So then the first instance, like x1 w1 plus x2 w2. Okay, so sometime let us forget about this bias. So we are not going to add the bias in this case. So then we will take this value. So in this case, like x1 is 1 and times 1 plus x2 0 times 1. So that is equal to 1. Okay. So for example, let us take another case. That is for second instance. Second instance x1, this is third instance. x1 1, x2 1. So if you substitute these values, then 1 times 1 plus 1 times 1 times 1, so that is equal to 2. Okay, only for like, and if you take a last instance, that is where x1 x2 equal to 0, then 0 times 1 plus 0 times 1, that is equal to 0. So if you observe, that is as per this equation, if you observe for all these kind of inputs, the value, that means 0 when both the inputs are 0, and the remaining, the 1 or 2. Okay, so these are the outputs. So we have to define a threshold, or whatever the activation function we are going to define. That activation function should be designed in such a way that it has to produce 1 if any one input is 1, or the sum is 1 or more. The sum is, like, suppose let us say a threshold is defined using, so threshold is defined using theta. So then the theta, that should be greater than or equal to 1. If the theta is greater than or equal to 1, then it has to produce 1 as output. If theta is less than 1, theta is less than 1, so less than 1, it has to produce 0. So if we define this threshold value, the activation function is defined in such a way, so then it always produce the correct output. So for example, this is for the two features, like two inputs, x1 and x2. Suppose there are 3 inputs or more number of inputs, and what would be the, how is there any changes need to be done in this activation function or the threshold? So let us take one more, and if you take three features or the 3 inputs, so then like the data set would be, the data set, so x1, x2, x3, and then y is the output. So for example 0 0 0 and 0 0 1 0 1 0 0 1 1 0 1 1, like that. So 3 ones, like that. So there will be 8 combinations, 8 inputs in the sense 8 samples will be there if you take 3 inputs. In that case also, like suppose, and the summation that would be expressed as x1 w1 plus x2 w2 plus x3 w3. So for example, here if you take w1 equal to w2 equal to w3 equal to 1, that means all weights are same. So when we need to update, why we need to take this constant weight or equal weights, and why we take this biases, like that you will understand later. So we are not going in detail because it's a very basic example, that is to understand the perceptron. So here in this case, for example, if you take any, like suppose if you take this instance 0 1 1, so 0 1 1 means 0 times 1 plus 1 times 1 plus 1 times 1, so it is equal to, so it's equal to 2. Okay, so here are the same, so no need to change the threshold value. And for this n number, for 3 inputs also, like that we can check for n number of inputs, is there any changes need to be done, so we can train this. So how, like suppose whatever this data we are using to train this or to build this perceptron to mimic like a logic gate of OR or AND, if any error occurs, then how and what need to be done? So that is because these are the simple, and we can easily represent this logic gates in terms of perceptrons. And if you take AND gate or any other logic gates, so suppose let us say there is an instance or a sample like 1, x1, x2, x3, there are 3 inputs and there is a 1 output, 1 0 1. Let us say the output is 1. So for this sample, while training this sample, so this activation function produced so 0 or some value which is not equal to the output, expected output or actual output. So that means the actual output, and there is a difference between the actual output and the predicted value. That means predicted value means the value which is returned by this activation function. So in that case, so we need to do this kind of a backward propagation. So let us just quickly understand what is the forward propagation and backward propagation. So later we focus more on these concepts. So as of now, just the forward propagation means the input is propagated from the input neurons and to the next, like suppose as we discussed in the previous lecture, if in the like artificial neural network, so there will be n number of layers and each layer is going to have a number of neurons, etc. So and the information is propagated, that is from this one layer to another layer. So this is the way, like each layer there will be a number of neurons each. So particular setup in each layer, all or may not the specific set of neurons will get activated. So then those are neurons will allow to flow the information to the next layer. So like that, the information is moved from the input layer till the output layer. So that is a forward propagation. Whereas backward propagation, that means, so like suppose if there is an error, that means output expected out what is the output and predicted output value. So there is a difference. So in that case, so there will be some error. The difference between this predicted value and expected value is not expected, it's original value. So if there is a difference, that is called as an error. So to minimize that error, so that error need to be propagated, that information need to be propagated back. So that is in this direction. So this while propagating back towards this direction, that is backward propagation. Here the weights, like suppose this is a simple neuron, but in the real world there will be a number of neurons in each layer. So here the information would be propagated towards back. So here in this process the weights would be updated and also the bias would also be updated. So like that, after updating, and then the model will be trained again, so that again we'll verify whether the output is correct or not. If it is still an error, so then it will be again, so the weights and biases need to be updated. So that is the one like one kind of just tuning the weights and biases, so that inputs and the corresponding outputs will match. So if it is like, if everything, that is the way we can train the models. So that means all the input and the corresponding outputs should match in the sense, suppose if you are given inputs like 0 1 0 and the corresponding output is 1, so it has to produce, the model should produce for each sample, it has to produce the corresponding output. If not, then there is some error. So that error need to be minimized or need to be nullified, so that we can build the model, perfect model. So then that will accurately predict the values. So this is the way we can design this perceptron, that is we can represent this logic gate like OR gate. And suppose if you take a AND gate, so AND gate, so if you take example of this and if you take the truth table, so you can also try other all logic gates or any other problems. So like suppose if you take AND gate, so and there are two inputs x1 and x2 and one output. So 0 0 0 1 1 0 1 1, these are the 0 0 0 and 1. Okay, 0 0 1. So in this case, how we can design this? So the threshold value, how we can define the threshold value such that it has to produce the corresponding output. So like suppose if you take a sum function, that is summation of all the inputs, weights are equal to 1, and this is output, and the summation like here 2 and 1 1 0. Okay, because we are not going to multiply here, so this is a summation function need to be applied. So based on that, and we can define the threshold value. So now how we can define the threshold value? In the previous case, like OR gate, we defined a threshold value, that is the theta. So theta, that is greater than or equal to 1, then it has to produce the output 1. If theta is less than, so theta is less than 1, it has to produce the 0. That is for to implement the OR gate. For any number of inputs, it is valid. But if the AND gate, and for two inputs, and how we can define this, the threshold value. So let us try to understand here. So in this case, like the total number of inputs, okay, so there are two inputs, the total sum should be 2 plus, that is all inputs are 1, then only it has to produce the output 1, and the remaining all the cases it has to produce the output 0. So that means the threshold value. So what will be the threshold here? So threshold means if it is greater than or equal to, so greater than or equal to 1, and it will produce the 0, it has to produce the output 1, not 1, greater than or equal to 2, because there are two inputs, so it has to produce 1. And if it is less than 2, so it has to produce the output 0. So this is for two inputs, x1 and x2. So suppose there are three inputs, so three inputs means like 0 0 0 1 0 0 1, like there will be, so then the total, the sum of the inputs would be 0 1 2 and 3. Okay, so in that case, so that means if all inputs are 1, then the sum would be equal to 3. So in that case, we can modify this threshold value, that is when the theta is greater than or equal to 3, then it has to produce 1, and the less than, theta is less than 3, then it has to produce 0 output. So that is the way we can define this the activation function or the threshold. Simply, if you want a threshold to, that is we can set, that is the to produce the output. So that's it. So in this lecture, we let us quickly recall what are the key takeaways from this lecture. So here we discussed mainly the numerical example of perceptron, that is mainly the threshold value, how we can define the threshold, and we discussed two simple examples like OR gate OR and AND gates. AND gates for 2-3 inputs maximum. So 2 or 3 inputs. And we also discussed mainly how the training. So training, like suppose if the output is not, the predicted value is not matching with the output, actual output, the predicted output and actual output, there is a difference. That means there is an error. So that error need to be minimized. So to minimize that error, so we have to do the backward propagation. That is, the error information need to be propagated towards the back there. So we use like the gradient, that is to update the weights and biases that we will discuss in detail later. And the forward propagation, that is the information is moved from the input layer to the output layer, whereas backward propagation is moved from the output layer, that is error information would is propagated back towards a back direction, so that the weights and the biases would be updated. So the model, that is a tuning would be done so that the model would accurately predict the output. So till that is we get the accuracy, much accuracy, then we have to keep on updating the weights. So till the expected output and predicted output is matches. So then, so that model, that is the model training part. Okay, so testing and validations will be discussed in the coming lectures. So thank you for watching this video.